Hello, this is Ted Wertheimer, and it's a pleasure for me to talk about what's new in the Marc 2017 release as part of the beta program. First, I'd like to thank all of you who are contributing to the beta program. We appreciate your feedback to make sure that we are giving you the technology to make you more productive and to be able to provide a quality product. So the Marc 2017 release is similar to our previous releases in that we always try to satisfy certain themes. The themes being nonlinear material behavior, contact, ease of use and performance, and advanced analysis. So we're going to see things in the area of material modeling and particularly data encryption and new data fitting algorithms. We're going to talk about really productivity tools in the area of contact. We're going to talk about a whole multitude of things in terms of ease of use and performance, and then some advancements in global adaptive meshing. So, of course, I'm going to start off with the area of contact because we know that's very important to the user community, and talk about first something in the area of contact interaction that people have been asking us for a long time. Namely, that you have a certain number of bodies, and what you'd really like to see is visualize what is the total force between bodies, or the total flux between bodies, and we can do that now in two ways. One is when you see the contact table menu, you can click on one of these boxes, and the entry values come up, and you can enter two additional nodes, one associated with each body. And if you do that, then in a post-processing mechanism, we can really visualize what is the total interaction force between these bodies during the mechanical process. This is also a very nice tool to look at free body diagrams of bodies in your structure. Normally, of course, we typically took a look at the model. This is our favorite manifold model, testing the gasket element, and we might have looked at the temperatures during that process or the stresses, and particularly the stresses in the bolts. But now what we can do is we can use this capability for doing time history plots where we don't look at the total behavior, but we look at the interaction behavior between bodies. So there used to be in the time history plot, the history option, there was a lot of scrolling that you needed to do if you had a lot of bodies. So the history menus have been substantially changed so that you would basically say, I want a global, my x-axis might be a global variable, in general time, and that's the default. And then you would easily select which body you're interested in or which body pair you're interested in. And in this example, we show the strain history, the strain energy, but we could do other things as well. And in particular, one that was asked for a lot was the thermal flux between bodies and the force between bodies. And we can also look at things like the contact area between the two bodies. Another advance on visualization has to do with associating a color with a contact body. So in this problem of a landing gear door, we have lots of bodies, and it used to be depending on what you had selected for visualization, either through the select option or through the model browser option, the colors would change on you. And that was very inconvenient when you were trying to do things because your mind basically associated a particular color with the body. That's no longer the case. The colors will remain fixed, whatever the selection options are, and the same colors will be used in post-processing as well. You can also, when you define the body itself, you can associate a particular color with it, or you can let the MenCat default colors to be used. Technology-wise, a big thing that was added was thermally driven contact. There really are two applications here. One is the first application where we have two bodies. They're normally in conventional contact, but they reach a certain temperature, and we want those bodies now to be glued together, typically in a welding type application. The second was we had two bodies and they were glued together, and then we wanted them to separate when we reached a certain temperature. So you could think about that as actually a glue between certain composite parts. And what it really means is if we look at the case of contact mode and bonding, we'd have no glue condition here, so things could slide relative to one another. Then it would reach a certain threshold. They would then be glued together. And if you didn't have a debonding threshold, then those bodies would stay glued. But you could also have a debonding threshold. Or just the opposite, if you had thermal breaking, you would have basically been in glued mode, temperature, it would then go into conventional contact sliding mode, etc. So here's a little example. What happens here is this part moves along. You can see it's initially glued, and then it reaches a certain temperature, and then it begins to slide. Might be easier to look at it here very closely. Here we see it's glued. One point or one area becomes a high enough temperature so that it exceeds the threshold temperature. That breaks the glue condition, and it slides along. So there are some new menus or new additions to the contact interaction menus. And really, you know, we introduced these contact interaction menus a few years ago, and we sort of knew there were going to be more and more types of physics associated with interaction, and that's what we're seeing here. We're seeing the bonding condition, transition to glued contact at a certain threshold temperature, or here the breaking condition, here the value wasn't entered. Or when you do a contact analysis, unfortunately something goes wrong, and often in support we say, well, use the print 5 capability or the print 8 capability and get more information. And what you would get is you get too much information. So now what we're doing is we're allowing you to control some of that by using some options on the print output menus. So you can say, I want print 5, I want more detailed information, but I only want it for a particular body. Or you could say, I want print 5 or print 8, but instead I only want it for a few selective nodes. Then you would go in here and say, instead of no node results, you'd select those nodes that you want the additional contact information to occur on. So it allows you to pinpoint things a little bit better than what was available before. So in the area of adaptive meshing, or I should say global adaptive meshing, two things have been done. One is more noticeable than the other, namely you can now do global adaptive meshing with higher order elements. This is very useful in problems where we have thin structures where really we don't capture the bending behavior very well with lower order elements, or in problems where we have a thermal situation and thermal stresses and thermal strains are taken into account better, more accurately with higher order elements. This is only available for the 10-node tetrahedral elements in 3D. We didn't think that this was such a critical problem for two-dimensional or axisymmetric analysis. The second thing is we've been working on improving the definition of the surface, especially the definition of the surface when you have multiple bodies and one of the bodies is adaptively remeshed and it's in contact with another body. But that's much more difficult for the user to actually visualize. So I'm going to show first this problem of a rubber analysis. It's a typical gasket type problem, and this is done with rubber. And because effectively this curved region over here, using the higher order elements, we can much better capture that geometry. And a simulation like this actually runs further using higher order elements than using lower order elements. We can also see in this case of crack propagation, here we can see the regions, the refined regions around the crack. We can see there are only 3 nodes per face. These are lower order tetrahedrals. And over here we have higher order tetrahedrals. So often we say that in the vicinity of the crack we want a better refinement of the stress, and so we can get that better refinement with the higher order elements. Of course, global adaptive meshing was often used for manufacturing applications in 3D. And here what we're basically seeing is we have a circular type punch, so that's a real quadratic surface. So using the quadratic elements, we can really exactly satisfy the contact condition and basically have greater deformation, less chances of penetration using the higher order elements. One should take some caution, though, that with using higher order elements, if the mid-side nodes are really not in proper locations, you're actually likely to get a inside-out condition because of the Jacobian of the element. So we can see that here in sort of a final plot. You really see that these tetrahedral elements have nice curved surfaces, and it truly satisfies the contact condition very well. The next area that we did a lot of work on, which is really evolutionary. I mean, we started with material curve fitting for rate-independent rubber materials, Mooney, Rivlin, and Ogden. And then we added more material data fitting associated with viscoelasticity and viscoelasticity for harmonic analysis, the so-called pain effect. And now we've added additional material data fitting for 3 types of models. One is general plasticity models, flow stress analysis. We want to look at what is the hardening, how does the evolution of the yield surface occur. So you can enter in stress strain data in what we call a ragged data format. And it can include stress strain data, it can also include strain rate effects, and it can include temperature effects. And then from the experimental data fit menu, you'd come down, you'd basically say plasticity, and then you would say the flow stress. And then effectively what would happen is you select one of these different models, so from 8 different models, and it would effectively curve fit your data, and then you could choose which is the model that is best representing my experimental data. And this is a little bit more in detail. Effectively what we see is after we've defined our ragged table through the tables option, that we then can basically select, in this case we just had strain dependent data, and here we're using the power law model. The green is the user entered data, the red is the calculated data, or the data after the coefficients are calculated. And if we take the same data and use, in this case, the Hockett-Sherby model, then in fact we even get a much better fit with our user-defined data. And as I mentioned, we can do this with a large amount of input. And here we see more typical type of data. It's not smooth, what comes out of your test equipment, but it has plastic strain, strain rate, and temperature. And again, we are doing this. This time we're using the Johnson-Cook model, which is often very appropriate for high temperature applications. And we have a whole stream of data. You can see the experimental and the fit data, but sometimes it's easier to use this plot data and say, I just want to see how well we fit a particular curve, or how well did we fit the data for a particular temperature, a particular strain. And you can see that with the Johnson-Cook, if I selected this particular curve, it did a very good job. And if I would have used the GMT Model 1 for that particular curve, it also did a very good job. In this case, most people would have probably used the Johnson-Cook model because they would have thought that that was more physics-based than these GMT models. Another set of material models, we've had the Hill Anisotropic Plasticity model in Marc for over 40 years. These newer bar lot models, which were really designed for aluminum, have been added over the last 5 years, but it was still very difficult to take experimental data and determine the coefficients. And now all those particular non-isotropic yield functions can be fit in MenTat, and then of course that data gets applied to your material behavior. And again, effectively you would have done the same sort of things. You would have entered uniaxial data. You would have entered these R values, which would have been your data looking at 0 degrees, 15 degrees, 30 degrees, 45, etc. The more you have, the better we're going to fit the data, and you would have basically determined the coefficients. The big one, which really goes to material model that was just really introduced recently, these parallel rheological framework models. Really designed for thermosetting plastics, but also designed for other materials, materials that have a large strain elasticity component. They have a rate-dependent part or viscoelastic component. They show upon unloading there's some sort of permanent set going on, and there might also be material damage occurring in the model. So you can take all those types of effects and try to represent it. And what you would do is you generate a table where now our independent variable is the time and our dependent variables are the strain and the stress, and you would effectively decide which type of physics you want to incorporate, and you can effectively tell it to determine the coefficients. One of the things I should have mentioned was really on both the plasticity problem and this parallel rheological framework model. Let's say you did an experiment on Tuesday and you got certain data, and then you repeated the experiment on Thursday and you got a different set of data. You can enter both of those sets of data simultaneously into the program through two different tables, and it will come up with the best curve fitting, best material data fitting for both sets of data. So in this example, what happened was we basically can think of this as time. We basically had one loop here. We unloaded it, went down this curve. We reloaded it here. We unloaded it over there. Reloaded it up here. We downloaded the back there. So you could think of at stress equals 0, you know, the intercept here is really the amount of so-called permanent deformation. And for this particular model, the input or the user data and our material curve fit data are really simultaneously on the same curves. So Doing plasticity data, work hardening data, very, very fast. Doing data for these types of complex models, it's likely to take 5 or 10 minutes, and it can take even longer depending on how much data you have. But of course, 10 minutes is really nothing compared to the fact that it probably took you months to be in the laboratory to get experimental data. Next thing we did having to do with materials is a continuation, also something that we introduced lately. We introduced that you can have your material data in an ASCII file. That was called the UMT file. We've extended that, so you can build up material models in Mentat, and then you can say write out an ASCII file, create an ASCII file. You can also have multiple materials in your model, and you can tell it to put all those different materials in the same ASCII file. So that's kind of useful. You know, when you're working as a team, you want to make sure everybody has the same material data, and that's what that allows you to do. The other thing what you can do is you can take that file and you can encrypt the file. And what that allows you to do is if you're a big company and you want your supplier not to see actual material data, use the material data, you can be provided with an encrypted file. Or you can do the opposite. Maybe you're a material supplier. What you could do is do the data, do the material curve fitting, provide an encrypted file, and then other people can use your material characteristics without seeing the detail. And these encrypted files, you can just encrypt them. You can encrypt them and associate it with a particular user or customer through the customer entitlement key, or what you can do is you can put in a time bomb that says this data is only valid for 1 year from now or for the next year. So you might say, well, I don't want that person to use that data 5 years from now because I'm not sure if I'm going to be manufacturing the composite in the same way. I'm not sure if my rubber compounding is going to be the same years from now. So if you have such a UMT file or a UME file, of course, when you are creating your model, you can read back in that file. You could read the file back in on a material by material basis, or if there are multiple materials in this file, you can basically go into the job menu and say, here's my file, apply it to all the materials that's appropriate. So one of the things that's associated with this is when people do this, they want to have longer material names. They want to not only just call it steel, but they want to give the ANSI standard on the steel. They want to say whether or not it's rolled steel or forged steel. So the file, the names associated with material properties, with geometric properties, with contact properties, if you're in the extended mode, have all been extended out to 160 characters. Another addition on material behavior has to do with the Lemaitre damage model. Often when people deal with damage models, they find that they get different results based upon their mesh. So we've introduced something what we call a non-local strain. So rather than looking at the plastic strain at a particular integration point, we come up with a smooth plastic strain, and then we use that damage model. So associated with that non-local strain is a certain length parameter. It has to do with the physics of the behavior. It really has to do with effectively in plasticity, what's kind of a dislocation range. So you'd have to specify that when you define your damage model, and then you would activate this non-local path option. And what it really is doing, it's doing a structural analysis and then a diffusion analysis. So we can see here an example. This would be, it was actually a notched axisymmetric bar, and this would have been the plastic strain. The scales are the same. This is the non-local total equivalent plastic strain. Here we have a bright yellow. We have very little bright yellow here. Typically, the non-local values are lower, and more significantly, the gradients are lower. So we can basically take a look at damage values, and then we basically see in terms of damage values and in terms of load carrying capacity, if the damage was used for influencing the Young's modulus or influencing the yield stress, there would be less variation with element meshes. Moving on to element technology, two enhancements have been made. One has to do with pyramid elements. A 5-node and a 13-node pyramid element for structural analysis and heat transfer analysis. In pyramid elements, we never really recommend to use pyramid elements, and a lot of people took a hexahedral element and they collapsed all the nodes into one node on one surface. That was a very bad thing to do because you actually developed a singular point there. So we've added these new elements. They're really used as transition elements between a hexahedral mesh and a tetrahedral mesh, as we'll see here in a minute. There are some limitations. You can't use subdivide with these elements, and local adaptive meshing and global adaptive meshing are not yet supported. So there are two ways of doing this. One is you have a parasolid geometry, and you say, from the parasolid geometry, do what we call hybrid mesh, which means a mesh with multiple element types in it, and generate the mesh. Or you can take the mesh and generate a surface mesh, and from there generate this hybrid mesh. When you generate it from the solids, what you'll get is a triangular mesh on the exterior that will generate lots of tetrahedral elements and will have few hexahedral elements. When you generate a surface mesh, you basically would say, I want a surface mesh that's predominantly quadrilateral dominant. We always have some triangles, and then generate the solids. So we're going to see this here in a couple of examples. This is kind of example I want to show. It's this block here. This is what the CAD structure, better representation of the CAD structure is. Here it was just tetrahedral mesh on the exterior. Here it was basically a quadrilateral dominant mesh on the exterior. If we look inside, just cut a line through it, okay? Then effectively what we'd see, actually this was using select, we'd see basically hexahedral elements in the interior, then pyramid elements, then tetrahedral elements. If we had our quad-dominant surface on the exterior, we'd have typically prism elements on the exterior, possibly some tetrahedral elements in between, and typically more hexahedral elements. You might say here your mesh was much thicker, but even if I would have made this a smaller mesh, that would have been true. So what I can do is I can kind of use something called model clipping, which we introduced in the last release, and we can actually step through this, and we can see how many are pyramid elements, tetrahedral elements, and hexahedral elements. And I'm just walking through the model. Might have been fast. That's always a challenge. And you can see how we move through and what the element type is in the problem. And even on these complex geometries, like this crankshaft, here what was done was the exterior here was done with triangular face. And if we step through, then what happens is we can see, and we'll cut it at a certain point where it's predominantly hexahedral, and you can see in larger regions, these are predominantly hexahedral dominant type meshes. The other area of element technology that we did was for piezoelectric elements. Piezoelectric elements are often used for control systems, but also used for in the acoustics area, either in loudspeakers or as impedance measurements. And we have a group of, these were the lower order elements, and now we have a series of higher order hexahedral elements and tetrahedral elements. Again, we felt that with 2D structures or axisymmetric structures, you can always use a finer mesh. Performance. Of course, everybody is doing bigger models. Everybody wants better performance. A couple of things were done. One was the use of a DDM, domain decomposition method, with MUMPS for a distributed computing environment. We combined this. We've done additions to the MUMPS solver so that it can be used out of core. And we've done something so that when it forms a global stiffness matrix, as we'll see in a couple of slides, it's doing it more efficiently. The other thing, which of course I recommend for everybody who's running the Marc product on a laptop or even a desktop machine, is to use the Paradiso solver and use parallelization. And before, we weren't printing out the singularity ratio, but as long as the system is a real, symmetric, positive, definite system, we are now printing out the singularity ratio. Okay, so how did DDM and MUMPS work before? What it used to do is it would distribute your domains out to different computers, and then on the so-called master computer, it would take the stiffness matrix for all those domains, including the stiffness matrix done on that particular processor. It would form a global stiffness matrix, and then it would redistribute that global stiffness matrix back to the separate computers. So this machine required a lot more memory, and we had a lot more I/O going on. And so now what we do is we form the domain stiffness matrices on each one of the machines. We form a global stiffness matrix, but we don't do it on a single processor. We know exactly how we're going to solve the system of equations. We distribute the assembly of the global matrix, and we solve it in a distributed manner. So less I/O, less memory required on the master processor. So this is a pretty large model. It's a giant engine block. I'm sorry that I can't share it with you, but it's 10 million degrees of freedom. And we first just looked at the first load case, which was bolt tightening. And you can see that the solver time used in the solver, first of all, the in-core and the out-of-core are almost identical, and you can effectively see that effectively we get somewhere a little bit over 5.5 times improved performance in the solver. If we look at the total wall time, then effectively we get a little bit over 3 times improvement, and again, the out-of-core doesn't cause a big penalty in terms of the wall time associated with the solver. Must admit that this was done on a machine with multiple chips between different machines and a high-speed internet communication. Okay, but this is what we were really trying to address. So this 10 million degree of freedom job used to be, if you wanted to run this in core in a serial process, it needed over 160 gigabytes. out of core in a serial process, now we can go down to as low as 60 gigabytes. But when we use parallelization and DDM and the distributed assembly, each one of those machines now can be as little as 20 gigabytes to run that particular job. So we don't need a large amount of memory on a given particular machine. Okay, ease of use issues. We did a survey. I thank you if you participated in the survey. The number one request was doing multiple undos. So we can now do multiple undos in the MenCat product. And the way you have to start this up is you actually have to go take a look at your little desktop icon and right-click on it and go into the properties. The easiest way to do that and set multi-undo equals on. Before we did undo through memory, now we're doing it on a disk, but we've significantly improved the speed associated with saving and reading reading MUD files. So what this means is now we not only have an undo symbol, because you might undo about 5 times, and then you would say, oh, that's not B, I want to go forward. So we have an undo and a redo icons on the top menu bar. Over the last few years, 2015 introduced defining boundary conditions on geometric entities, parasolid entities. Didn't matter if you read in a CATIA file or a SolidWorks or whatever. Internally in MenCat, it was always parasolid, similar to what it is in PacTran or Apex. And we could apply the boundary conditions on those entities. Now we have a much more tighter integration so that we actually kind of bring some of that solid information into the solid, into the solver, so you can see we're in post-processing mode. We have some new sets that talk about the solid faces. So this was a little coupled analysis, and I applied a film load on these surfaces. Wasn't perfect because I missed a few surfaces, but now we can quickly see that in terms of the parasolid representation that's in the on a post-processing side. We can look at that also here. This is one of our standard models. I think it's volume E842. But here it was reconstructed. So it was reconstructed using CAD entities. And particularly, there are 4 wire entities, 1, 2, 3, 4. And there are 2 sheet body entities, the metal sheet itself, different use of the word sheet in this region here, and we can see those geometric entities in MenCat in pre-processing phase, and we can also look at that in terms of contact bodies, so we combined a bunch of sheet entities into one contact body. And then when we're in post-processing mode, so here I'm at increment 271, what I can do is I can look at the model in terms of my finite element entities, but I can also, by using in post-processing a button that's been there for a long time, but it's now much more powerful, we can draw the geometric entities in post-processing mode, and we can look at the CAD geometry both as it originally came in and its final configuration. I hate to use the word deformed configuration because those CAD representations, of course, don't really deform. It's the finite element representation of the material where the deformation occurs. So all these things mean a lot of changes in the Marc input file and also changes on the post file. So we have a new input format for the Marc 2017 release. It's called the version 13. We have some new option called CAD bodies that introduces this CAD concept. And so the key thing is that this is a CAD body, and it's CAD body is number one, but associated with it are 4 numbers. So when you introduce your model into Mentat, if you say this CAD body is used for contact, or this material is associated with this CAD body, or this orientation is associated with this CAD body, we're going to use that later. And what we're going to do is, this is actually the different examples of it here. Here we have connectivity associated with a CAD part. So there's some additional lines or additional numbers. This number 1 says these group of elements, and you'll see Mentat will write out different blocks of elements if they're associated with different CAD bodies. We'll say this bunch of elements are associated with CAD body 1, and then it will say CAD body 1 happens to have material ID 1 and contact body 1. Okay? Here what we did was there's no CAD body. We're just going to say there's a bunch of connectivity, and we're going to associate with each one of these connectivity. We're going to say this group has material ID 1, and this group has contact ID 1. We also have some new sets because it's geometrically based, it's parasolid based, and those sets look like I'm defining a CAD phase set, and I'm calling it some boundary condition on solid faces, not on surface faces that we did before, but on solid faces. And that influences the attached node because we can now have the node associated with a CAD vertex. It's used with the attached face option. It's used with the attached edge option, so we can associate finite element edges with a wire or an edge associated with a CAD body, and attached face again. So if we do all this, everything's now geometric CAD oriented. When we see the material properties, material option, we don't see any more element numbers. We don't need to give the element numbers because when we gave the connectivity, we associated the material ID with the connectivity. In some sense, it's much closer to what we do with MSC Nastran when we have IDs on things like the C quad 4 option. But in fact, it's a little bit more general than that because we can associate more types of quantities with these things. So I'm going to finish up with this, with the last of the important information. Obviously, there's a sign-up, and I think all of those on the call have probably clicked through and signed up for the beta. We anticipate the beta to be available tomorrow, March 31st, and if you're on certain time zones, you might not see it until the following Monday. We'd appreciate your feedback associated with the beta release by May 31st. One of the things that we've done is on the product information document. We strongly recommend reading the product information document. It kind of gives a nice summary. So if you're interested in a particular feature, what is it that we think is useful for you to test, and where do we think the documentation is provided? If you need some help, of course, you can always contact your local support team, or you can reach out to Dr. Audrey Bout, who's head of Marc Product Development, or Gaurav, who's responsible for quality assurance, or myself, or Farnaz, who's working in the world of marketing. Or you can post your comments, inquiries through the Marc Beta Forum, which you can learn from others, or we will respond to that as quickly as possible. So with that, I'd like to thank you again for participating in the Marc Beta program. And if you have any questions, I'll be happy to answer them.